Hello everyone, let's revise 2D flows. First, let's define incompressibility and irrotationality. A fluid flow with velocity field u is incompressible if the divergence of u is equal to 0. A fluid flow with velocity field u is irrotational if the curl of u is equal to 0. If the flow is irrotational, we can find a velocity potential phi of x, y and z such that u is equal to grad phi, i.e. u is equal to the partial derivative of phi with respect to x times x bar plus the partial derivative of phi with respect to y times y bar plus the partial derivative of phi with respect to z times z bar. Now, let's define volume flux. For a given flow field u of r and t, the volume flux through a closed curve C is the volume of fluid which passes through C in a unit time, which is given by the contour integral around C of u dot n dl, where n is the outward unit normal to the curve C and dl is the element of length along the curve C in the direction tangential to C. Next, let's define circulation. For a given flow field u of r and t, the circulation around a closed curve C is defined by gamma which is equal to the contour integral over C of u dot dl, where dl is equal to t dl, which is the element of displacement along the curve C in the direction t tangential to C. Then let's talk about 2D flows. In this part of the module, we restrict attention to 2D flows, where u is equal to u of xy times x hat plus v of xy times y hat. If the flow is irrotational, then we can find the velocity potential phi of xy such that u is equal to the partial derivative of phi with respect to x, and v is equal to the partial derivative of phi with respect to y. For an incompressible flow, we can write the velocity in the form u is equal to the partial derivative of psi with respect to x, and v is equal to minus the partial derivative of psi with respect to y, where psi of x and y is known as the stream function. Following on, let's discuss some results for 2D flows. The lines psi equal constant are the streamlines of the flow, i.e. the lines which are tangential to the fluid velocity at each instant in time. Since fluid flow is tangential to an impermeable boundary, the boundary is a streamline, and so psi equals constant on a boundary. Any streamline can be replaced by an impermeable boundary without changing the flow. In this part of the module, we only consider time-independent flows, in which case the streamlines and the particle paths are the same. And, as ever, thank you for watching.